Geographically referenced data consist of any type of measurement or observation, whether analog or digital, which have a known distribution across the surface of the ground and hence can be represented as a map or section. Data of this sort are fundamental to all phases of mineral exploration. Any map is an example of a geographic information system, commonly known by its acronym GIS. However, today GIS is more specifically understood to refer to georeferenced data that is stored digitally on, then manipulated by a computer software. Understanding the meaning or usefulness of a particular dataset often requires that different types of map data need to be compared. This is a process of integration and is one of the fundamental ways in which data can be converted into knowledge. For example, a map showing surface geological observations may need to be combined with geophysical or geochemical maps for the same area in order to produce a composite map that will facilitate geological interpretation. This interpretation may then need to be overlaid on a land use map to check on access details or an existing drilling program map to see what previous exploration had been carried out on the area. This integration of different datasets used to be done manually in the past by overlaying various categories of maps, which is tedious, time-consuming, and impractical, especially with large datasets. GIS, however, offers a solution to this problem through its powerful way of handling huge datasets and presents them in a form that facilitates interpretation by the explorationists. Here is how GIS works. Different types of data for the same area are stored by the system on separate layers with reference coordinates, providing the link between information on the different layers, and once in electronically stored digital format, the datasets can be enhanced, searched, compared, combined, presented at any scale, displayed on a monitor as a 2D or 3D image, or printed as required as hard copy maps and sections. To perform a task using GIS, basically there are four main procedures. Number one, data entry. When manual entry of data has been involved in producing computerized databases, errors are expected. So checking for such errors or any other sorts of inconsistencies within the data is a vital part of any data entry process. Remember that the quality of the output is determined by the quality of the input. As the saying goes, garbage in, garbage out. Number two, data validation. Usually, digital map data such as remote sensing imagery, most geophysical and geochemical measurements, or isolated whole color locations are already in a natural form for electronic storage in a computer. However, analog data such as geological maps and aerial photographs can be converted into digital format for electronic storage through processes like scanning, digitizing, etc. Number three, data manipulation. GIS allows the data to be manipulated in a number of ways, like search operations can be done for different attributes. Selected ranges of numbers can be highlighted. The position, size, and attribute of different map areas can be compared both within the same layer or between different layers. Different types of data can be combined into one layer or image. The purpose of such composite images is to facilitate visual recognition of key correlations between datasets. Moreover, there is a set of geoprocessing tools by which geospatial analysis can be done. For example, analytical geoprocessing operations like clipping, buffering, intersecting, unifying, etc. come in handy to the aid of the explorationists interpreting their data. Number 4, data presentation. The computer can do a lot of essential processing of digital data, but once this is done, qualitative interpretation requires conversion of data into map format. Map presentation makes use of the power of the linked eye and brain system to distinguish patterns and spatial relationships in complex datasets. GIS can offer various ways of doing this. Generally speaking, GIS allows geologists to present lithologies through the vector model, which is a model that presents real-world features through points, lines, or polylines, and polygons used exclusively for discrete features, which are those with noticeable boundaries between them. Geochemical concentrations and geophysical data can be represented using contour maps or sections. Another powerful GIS model for presenting spatial data is the raster model, designed for continuous features in which the change in values is gradational, and in both cases vector and raster models a complete set of functions for the layout process with all of the cartographic elements of map design is available in GIS. What really makes GIS an attractive tool for exploration geologists is its capabilities that now allow full possibilities of integrating industry-standard relational database management system, 3D visualization, geostatistical functionality, 3D geoprocessing capabilities, and web-based mapping. Now geologists are able to collect field data electronically using global positioning system receivers and ArcPad. In addition, all types of geological datasets, such as geological maps, geochemical, geophysical, and boreholes data can be displayed, interpreted, and presented by GIS. In fact, data presentation, visualization, and geospatial analysis in general have become easier and more powerful with the advent of open source GIS, which is a free GIS software, and through it basically anything can be done, from using geodatabases, modifying them, and creating your own maps. Examples of open source GIS software are QGIS, Map Window, Saga GIS, and Whitebox. Today, web mapping or web GIS is a huge business with super advanced, sophisticated functionalities for creating and publishing geospatial data utilizing a plethora of software packages and programming languages.